So, if reverse phase chromatography is so great, why do we need to talk about normal phase? That's a serious question.
Well, if you have a compound that's not stable in water.
How about if it's not soluble in any polar solvent like methanol? And there certainly are organic compounds that are pretty darn non-polar, that don't dissolve well in methanol. Then for sure you got to do normal phase. I'll just throw one out. Carotene. I'm not a food scientist. Megan? How big is carotene?
I don't know.
It's either 24 or 32 carbons long. I know that. It could be 26 or 28. It's just loaded with double bonds, and simple carotenes have no polar functional groups. Not very soluble. It's nicely done by normal phase chromatography. If you do it by reverse phase, it's like 95%. Use hexane and ethanol as the mobile phase. That's hardly a reverse phase, mobile phase. And you use a bonded phase as the stationary phase. It's not really reverse phase, but they call it reverse phase. So that's one reason. If the compounds are unstable in water, if they hydrolyze in a heartbeat, likely they'll react with an alcohol as well as water. But normal phase does offer some selectivity advantages, especially for polar isomers, that makes the separations by NPLC a lot easier than by reverse phase. So one ought not count normal phase liquid chromatography down and out. And various surveys indicate that it may represent 10–15% of the population of methods that are developed. This isomer selectivity, is related to, comes about due to the geometry of the solid surface, which I'll talk about in a second. One very important aspect of normal phase liquid chromatography is that the amount of water that gets into your eluent has an enormous, can have an enormous effect on retention. And I've always said this every time I've taught this material, and I've had graduate students in my lab neglect it and not get reproducible results, not get reproducible results, not get reproducible results, until they dried their solvents. And I mean really dried their solvents. You cannot imagine how serious this effect is. It is sometimes very difficult to get reproducible results by normal phase. And I think that's part of the downside of it. But you can do it if you recognize what the problem is. Okay, to understand normal phase, we're going to have to talk about adsorption models. The simplest model of adsorption is the Langmuir monolayer model. And I think we all really need to know about it in some detail. And the basic model that, by and large, has won out over the last 25 years is the Snyder model of normal phase LC, which really helps us predict retention in normal phase. So we're going to spend a good bit of time talking about it. Here's what I mean about selectivity. Here's a lumina stationary phase. I don't remember what the mobile phase was. I think it might have been hexane. But here's 4 polar compounds. I'm going to look at the alpha relative to the 2-methoxynaphthalene. These are really nice alpha factors. You could maybe even do this in a test tube. Forget about a column. You won't get alpha factors this big for these compounds in reverse phase. If we look at the number of polar functional groups, so we got a monomethoxy and a dimethoxy derivative here. That's an impressive alpha. Mononitro, dinitro, impressive alpha. Two different polar functional groups, nice alpha. Bromo group is not an especially polar functional group. I just don't think you're going to see anything like that in reverse phase. I'm not saying you can't separate meta and para dibromobenzene by reverse phase. I think you can. It's a pretty tough separation. You need a very efficient column. It can be done. But this is an easy separation. Quinoline and isoquinoline, that's a fantastically easy separation. And this is my favorite case. These two compounds have the same number of aromatic rings. It's just a question of how they're put together. But that's an awfully nice alpha to work with. So sometimes normal phase gives you a selectivity that you just can't get by reverse phase, and it makes your life really easy. And the better the alpha factor, the faster you can do the separation. You just don't need that many plates, so you can use a really short column. The reason the geometry of the molecule matters so much is that the sites on the surface of the silica or the alumina can't move around. They're fixed. The geometry is absolutely rigid, unlike a bonded phase, which has got lots of flexibility. And the bonded phase can change its conformation to maximize its interactions with the nonpolar parts of your solute molecule. So it can't differentiate them quite as readily as something that's absolutely rigid. And there's all sorts of ways that can happen. One of the big effects is the effect of water in the eluent on retention. Here's a chromatogram of these aromatic ring compounds running from benzene to meta-tetraphenyl. Meta-tetraphenyl, so it's benzene, biphenyl, terphenyl, ortho, and meta-tetraphenyl. This is the chromatogram that you get if you use hexane that's saturated with water. No retention. No separation of anything. This is the separation you get when you got hexane dried with molecular sieves. Scrupulously dried stuff. The fourth and fifth compounds are over there somewhere. They're really retained. This is what you get if you take 2 volumes of scrupulously dry hexane and mix it with hexane that was carefully saturated with water. I don't mean there are droplets of water scattering light in this hexane. It's been carefully equilibrated with water. 1 part, and you can see these compounds, which are over there, are now coming out. So if you have a highly activated polar adsorbent and you've got a very non-polar mobile phase like hexane, you're going to have tremendous sensitivity to minor amounts of water. And you're going to have trouble getting reproducible results if you allow the water that's in your solvent to change from day to day. Try and remember that if you ever do any normal phase looking chromatography. It will save you weeks. Okay, let's talk about the Langmuir adsorption model. So a Langmuir adsorption model is a little bit like a lattice model on a surface. So in a liquid, we have adsorption sites. So here's an adsorption site. Think of it as a polar group on the surface, like an OH group on a silanol. And at a low concentration of solute X in the mobile phase, some of these surface sites are going to be occupied by X molecules. But otherwise, they're going to be occupied by whatever your mobile phase is. Initially, let's keep it simple, and we'll make believe that we have a mobile phase that is a pure solvent, and we've got a dilute solution of our analyte X in that mobile phase. Later on, we'll get to solvent mixtures. So these sites are just solvent sites on a polar site, and this is where we have an analyte that has become adsorbed on the polar site. If we have a fixed number of sites on the surface and we say that adsorption is limited to one monolayer, then eventually all the sites on the surface get filled up and you can't adsorb any more stuff. The site is saturated with the analyte, with X. So basically the Langmuir model makes a number of assumptions. Number one, it says there's a fixed number of sites and that all of the sites are identical. It assumes that the sites do not interact with one another. So suppose I have this guy adsorbed on that site there. If the sites don't interact with one another, then the probability of adsorption here next to this is the same as the probability of adsorption over here, where there's no site nearby that also has an X on it. So there's no lateral interactions on the surface. The sites are all absolutely independent. That's clearly an approximation. Okay, and then we assume that the adsorption process stops at a monolayer, which is not necessarily the case. There's very many situations where you get bilayer and multilayer adsorption, especially in the gas phase, but bilayer and multilayer adsorption is also possible in the liquid phase. That's the basic Langmuir model. So here's our analyte or solute. Here's our site on the surface, and we're forming some kind of interaction between the analyte and the surface site. The simplest way to think about this is to start with the kinetic model, and so we're going to say the rate at which X species sit down on the surface, the rate at which they leave the solution is a rate constant times a bimolecular interaction between X and S, the collision, and then XS has the possibility of dissociating, and X goes back into solution. Given enough time, the system goes to equilibrium, and at equilibrium, the rate of change of concentration of X, either on the surface or in solution, goes to 0. So we set that equal to 0, and we can derive the equilibrium condition. And at equilibrium, this equals this. We can rearrange that into this form by taking the equilibrium constant to be equal to the ratio of the adsorption rate constant to the desorption rate constant. So this is the basic equilibrium expression for the Langmuir process. So we're going to combine this equilibrium constant with a conservation of number of sites on the surface equation so that the unoccupied sites S plus the occupied sites XS have to add up to the total number of sites on the surface. We combine this equation with this equation, and the concentration of occupied sites at equilibrium is equal to the total number of sites times the equilibrium constant times the concentration of X in solution at equilibrium divided by 1 plus the equilibrium constant times the equilibrium concentration of X. We can define a fraction of sites occupied by taking the number of occupied sites and dividing it by the total number of sites and plot. So a plot of the fraction occupied versus the concentration, I should have written that as concentration of X, divided by the equilibrium constant for adsorption, is going to look like this for the case where N0 was 10 and the equilibrium constant was 1. And if you look at this, when the concentration X is equal to 1 over the equilibrium constant for binding, half the sites are occupied. You keep going up and up and up in concentration, the surface gets saturated, all sites are taken, you can't adsorb anything else. Overall, the binding isotherm is nonlinear, but we know that we're not going to do chromatography where it's nonlinear. We're going to do chromatography way down there where it's linear. That's the basic Langmuir monolayer model. This really informed a lot of Snyder's thinking about normal phase. But in order to come up with equations relating and predicting retention, he made a lot more additional assumptions. This first assumption is really pretty consistent with the Langmuir model. The surface is homogeneous and is only one type of site. He went on to assume that all the adsorbates, the adsorbate is the stuff that's undergoing adsorption, the analytes, the solutes, interact with this type of site by the same types of intermolecular forces, regardless of the adsorbent surface activity. We'll talk about what surface activity is in a few minutes, but basically it relates to how strong are the adsorption sites. Snyder's going to assume that the surface is planar, flat, and he's going to assume that all sites are equally accessible to all groups on the molecule. Now, surfaces are not flat, especially when they're in porous solids that have pores of 50, 60, 80 angstroms. So this is a pretty dicey assumption. So the adsorbent is homogeneous, only one type of site exists. All adsorbates interact with this type of site. We went through that. We went through this. This is the biggie. at some point, Snyder, in order to come up with tractable equations, but tractable equations that make reasonable predictions, he is going to assume that the interactions in the mobile phase, that is, the interactions between the mobile phase and the stuff dissolved in the mobile phase, those interactions are weak, small, compared to the interactions between the solute and the adsorbent and the surface, and between the solvent and the adsorbent. He's completely blowing off all of the chemical interactions and the physical interactions going on in the mobile phase. All the action takes place between molecules that are on the surface and the surface. Now this is really radically different than what goes on in a partition model. In a partition model, it's the interactions between the molecules in the mobile phase and the molecules in the stationary phase that make things happen. And you can't neglect one versus the other. Here he's saying, forget about the interactions in the mobile phase. But let's dig in here a bit, because it's very, very important. Something will undergo partitioning, transfer from one solvent to another, depending upon how soluble it is in those two solvents. That's what will control the degree of transfer. In adsorption chromatography, what makes a solvent a good